Listen closely, because what you are about to hear is not a story about a broken telescope or a misread number on a graph. It is a story about a law that every single one of us trusts with our lives, every single day, without ever questioning it. A law so fundamental that physicists treat it almost like a sacred text. It is called the Second Law of Thermodynamics, and it makes one simple, unbreakable promise. Disorder always grows. Spilled milk never crawls back into the glass. A shattered window never reassembles itself in reverse. The universe, left alone, drifts from order into chaos, like a sandcastle slowly losing itself to the tide. This is not just a rule of physics. It is the reason time has a direction at all. It is the reason you remember yesterday but cannot remember tomorrow. It is, in a very real sense, the arrow that points from birth to death, from order to dust, for every star, every civilization, and every law book ever written. And then, somewhere in the deepest, oldest light the universe has ever sent us, we found something that should not exist. We found structure, real, complex, breathtakingly organized structure, sitting exactly where the textbooks insist there should have been nothing but a formless, chaotic fog. We looked back toward the very beginning of time, expecting to see the universe's messy, half-built nursery. Instead, we found something that looked disturbingly like a finished room. Galaxies, fully formed, fully grown, sitting calmly in an era when, by every calculation we trusted, they should have been nothing more than scattered bricks waiting for a builder who had not yet arrived. This is the moment scientists do not talk about at dinner parties, because it terrifies them quietly, in the way only a true crack in the foundation can. Not a flashy explosion, not a dramatic collision, just a number that refuses to add up, a timeline that refuses to behave, a universe that appears to have done its homework before the class even started. Today, we are going to step into that crack. We are going to ask the question that some physicists whisper and others refuse to ask out loud. What if the second law of thermodynamics, the law of inevitable chaos, is not as absolute as we have been told? What if, in the earliest moments of existence, the universe broke its own rules? Or worse, what if it was never truly playing by them in the first place? To understand how strange this is, we have to leave the world of equations for a moment and step into something your body actually understands: scale and the brutal honesty of probability. Imagine you are standing in a quiet room holding a brand new jigsaw puzzle. 1 billion pieces, not a typo. 1 billion. A puzzle so large that if you laid every piece edge to edge, it would stretch across an entire continent. Now imagine you open the box and instead of sorting the pieces, organizing the edges, hunting for the corners, you simply turn the box upside down and let gravity do whatever it wants. The pieces fall. They scatter across the floor in a chaotic, meaningless heap, exactly the way the second law of thermodynamics says they should. Disorder is the natural state. Order takes work, time, and effort to build. Now here is the part that should make the hair on your arms stand up. Imagine that exactly 1 second later, before the last piece has even finished bouncing on the floor, you look down and the puzzle is complete. Not roughly complete, not partially sorted, fully assembled, image perfect, every piece interlocked exactly where it belongs, as if 1,000 invisible hands had been waiting in the dark, ready to act the instant you let go of the box. Your mind would reject this. Your gut would scream that something is deeply, fundamentally wrong with the universe you thought you understood, because nothing in your lived experience, nothing in 300 years of physics, allows chaos to reorganize itself into perfect order in the blink of an eye. This, almost exactly, is the scale of the problem astronomers are facing when they look at the early universe. Cosmology tells us that right after the Big Bang, The cosmos was supposed to be the ultimate version of that dropped puzzle box, a hot, violent, nearly featureless soup of particles, far too disordered, far too young, far too chaotic to have built anything as intricate as a fully formed galaxy. Galaxies are not supposed to be quick. They are supposed to be slow, patient accidents of gravity, taking hundreds of millions, even billions of years to pull themselves together from formless gas into glowing, structured spirals of stars. That is the timeline written into nearly every cosmology textbook on this planet. Build the puzzle slowly, piece by piece, over a span of time so long that human history is a single grain of sand on its beach. But we did not find a half-finished puzzle when we looked back toward the dawn of time. We found something that looked suspiciously close to a finished picture, sitting on the floor only a few 100 million years after the box was supposedly dropped. And in the language of cosmic time, a few 100 million years is not a long wait. It is barely the time it takes for the universe to catch its breath. Consider another way to feel this same wrongness, this time not with a puzzle, but with something closer to home, a single human life. Imagine watching a documentary about a newborn child, and in the very first scene, only seconds after birth, that same child is shown delivering a graduate lecture on quantum mechanics, fluent, articulate, completely composed. You would not simply find this surprising. You would assume the footage had been faked, that something had been spliced together incorrectly, that the timeline itself had been tampered with, because nothing in your understanding of how growth works allows infancy and mastery to occupy the exact same breadth of time. And yet, this is essentially the situation cosmologists found themselves staring at when they pointed their instruments toward the deepest, oldest light in the observable sky. This is where the James Webb Space Telescope enters the story, not as a simple camera taking pretty pictures of swirling gas clouds, but as something closer to a forensic investigator standing over a crime scene that physics insists should not exist. James Webb was specifically engineered to look further back in time than any instrument humanity has ever built, because light itself is a kind of time machine. The light from a galaxy 10 billion light-years away did not just travel 10 billion light-years through space. It traveled 10 billion years through time, carrying an ancient photograph of a universe that, in many cases, no longer even exists in the form we are seeing it. When James Webb pointed its golden mirrors into the deepest, darkest patches of sky, it was not looking for nearby stars. It was reading the universe's earliest diary entries, and what those diary entries revealed broke something. Astronomers expected to see the cosmic equivalent of toddlers, small, clumsy, barely formed proto-galaxies, the construction sites of the universe, scaffolding and raw material with no real shape yet. What they found instead were galaxies behaving like adults. Massive, luminous, surprisingly structured galaxies existing at a point in cosmic history when, according to the standard model of how the universe builds itself, they should have barely begun gathering their first handful of stars. Several of these galaxies appeared so unexpectedly large, so unexpectedly mature, that some researchers half-jokingly, half-nervously began calling them universe breakers, because their very existence seemed to threaten to break the model that predicted them in the first place. Picture this in a way your body can feel. If the history of the universe were compressed into a single calendar year, with the Big Bang happening at the very first second of January 1st, then these mature, fully structured galaxies are showing up in the first few hours of January 2nd. Not spring, not summer, the very next morning. It is the equivalent of a human baby being born and then standing up, speaking fluent sentences, and walking out the hospital door before the nurses have even finished the paperwork. This is the crack in the wall we are here to examine. Because the second law of thermodynamics is not just about spilled milk and shattered glass. At the deepest level, it is intimately connected to something physicists call entropy, a kind of cosmic bookkeeping system that measures disorder, randomness, and the number of ways a system can be arranged. A simple, smooth, undifferentiated soup of particles is considered low in complexity, but in a strange twist that confuses almost everyone the first time they hear it. Surprisingly high in entropy because there are countless ways to arrange a formless soup and have it still look like formless soup. A galaxy, on the other hand, with its spiral arms, its central black hole, its billions of stars locked into careful gravitational order, represents an extraordinarily specific, extraordinarily unlikely arrangement of matter. Building that kind of order out of chaos should be slow. It should be the cosmic equivalent of climbing uphill, fighting against the natural tendency of everything to fall apart rather than come together. So when the deep past shows us order arriving far too early, far too efficiently, far too quickly, we are not simply looking at an interesting anomaly to footnote in a research paper. We are staring directly at a question that strikes at the foundation of how we believe time itself behaves. Either our understanding of how fast galaxies can form is dramatically wrong, or our understanding of how matter behaves in the earliest moments after the Big Bang is missing something enormous. Some hidden hand quietly tilting the odds, helping disorder collapse into order far faster than blind chance and patient gravity should ever allow. Now, before we go further, it would be irresponsible of any honest observer to claim that physicists are ready to throw out 300 years of thermodynamic law because of a handful of unexpectedly bright smudges of light at the edge of the observable universe. Science does not work that way, and frankly, it should not. Extraordinary claims, as the old saying goes, require extraordinary evidence. But what we can say with complete honesty is that the gap between prediction and observation here is not small. It is not a rounding error. It is a structural mismatch that has sent cosmologists scrambling back to their models, checking their assumptions, and in some cases, quietly proposing ideas that would have sounded like science fiction a single decade ago. Let us walk through the spectrum of explanations currently on the table, starting with the most cautious, most conservative possibilities, and ending with the ideas that genuinely unsettle even seasoned physicists. The first and most conservative explanation is, in a strange way, the most boring and also the most comforting. Maybe we are simply bad at counting light. Galaxies in the extremely early universe are unbelievably faint, distorted by billions of years of travel, and difficult to measure with total precision. It is entirely possible that some of these galaxies are not as massive as they first appeared, that errors in measuring their distance, their brightness, or the amount of dust obscuring them have inflated their apparent size and maturity. Surveys built specifically to hunt for this earliest light, deep field campaigns peering into patches of sky no larger than a grain of sand held at arm's length, returned image after image of galaxies that simply should not have been ready yet. Bright, compact, surprisingly massive systems, sitting in an era cosmologists had nicknamed the Cosmic Dawn, a period meant to represent the universe's first, fumbling attempts at building anything at all. Instead of fumbling, the early universe appeared to be working with practiced, almost suspicious efficiency. Several research teams have already revised early estimates downward as better data arrived, finding that a portion of the so-called universe breakers were, in fact, somewhat smaller and less catastrophic to the model than first feared. This is real science doing exactly what it is supposed to do, correcting itself in the face of new evidence. But here is the uncomfortable truth that conservative explanation cannot fully erase. Even after careful revisions, even after stripping away the most exaggerated claims, a meaningful number of these early, massive, surprisingly structured galaxies remain. The anomaly shrinks, but it does not vanish. And when an anomaly survives correction after correction, scientists start looking past simple measurement error and towards something deeper in the physics itself. This leads us to the second explanation, more daring but still grounded firmly within the existing framework of cosmology, the possibility of early dark energy. Dark energy, as most of us have heard, is the mysterious force believed to be accelerating the expansion of the universe today, pushing galaxies apart faster and faster as time goes on. The standard assumption has always been that dark energy was negligible in the early universe, a minor background character that only became important much later in cosmic history. But what if that assumption is wrong? What if, for a brief, violent window shortly after the Big Bang, dark energy surged with unexpected strength, then faded again, leaving almost no trace except for its fingerprints on how quickly structure was allowed to form? If early dark energy existed, even briefly, it could have subtly altered the expansion rate of the infant universe in ways that made it easier, faster, more efficient for matter to clump together into galaxies. In essence, it would not have broken the rules of thermodynamics so much as it would have changed the playing field those rules were operating on, like quietly tilting the table so the puzzle pieces fall into place faster than they ever could on a flat, predictable surface. This idea is taken seriously not because it is comfortable, but because it elegantly resolves several other unrelated tensions in cosmology at the same time, including the long-standing disagreement over exactly how fast the universe is expanding today, a separate mystery known among astronomers simply as the Hubble tension. When one strange idea quietly helps explain two or three unrelated mysteries at once, scientists tend to lean forward in their chairs. What makes this hypothesis particularly seductive is its restraint. It does not ask us to abandon the second law. It does not ask us to imagine some exotic memory bleeding through from a universe before our own. It simply asks us to accept that one additional temporary ingredient was present in the cosmic recipe, active only for a fleeting moment, then gone, like a catalyst in a chemical reaction that speeds everything along before quietly disappearing from the final product. The challenge, of course, is that nobody has yet found direct, independent proof that this ingredient ever existed. It remains, for now, an elegant patch stitched over a wound we still do not fully understand. Then there is the third explanation, the one that moves from daring into something closer to radical, the one whispered more cautiously, often hedged with careful language, because it touches something almost philosophical at the core of physics. The idea that the universe may carry some form of memory from a cycle that came before it. In certain models of cosmology, the Big Bang is not treated as the absolute beginning of everything, the moment time itself switched on from nothing, but rather as a kind of cosmic reset button, one chapter ending so another could begin. In these cyclic or bouncing universe models, our current expanding cosmos may be the latest iteration in an endless, repeating sequence, where a previous universe collapsed inward upon itself before rebounding outward again into a fresh expansion. Our expansion, the one we currently call home. If something like this is true, then the assumption that our universe began as a perfectly smooth, perfectly random, perfectly disordered soup may itself be flawed at its root. Instead, the earliest moments after the bounce could have inherited faint structural seeds, gravitational ripples, density patterns, organizational tendencies left over from whatever existed before the collapse, like a sculptor's chisel marks surviving faintly beneath a fresh coat of paint. The puzzle, in other words, may not have started from a truly empty box. It may have started already partially organized, carrying a quiet inheritance from a universe we will likely never directly observe. If this idea sounds uncomfortable, it should. It suggests that the arrow of time, the very concept that disorder must increase from a state of pure maximum chaos, may not apply cleanly to a universe that never actually began in pure maximum chaos in the first place. It suggests that what we have been calling the beginning may, in a very real sense, not have been a true beginning at all, but rather a continuation wearing the disguise of a fresh start. Some theorists go even further, proposing that the very smoothness we observe in the oldest background radiation, the faint afterglow of the early universe that fills every direction of the sky in near-perfect uniformity, might itself be a kind of scar tissue, evidence of a prior collapse so violent that it erased almost everything except a few stubborn whispers of structure. If true, our universe would not be a blank page at all, but something closer to a palimpsest, an old manuscript scraped clean and written over, where faint traces of the previous text still bleed quietly through the new ink, shaping how the first sentences of this chapter were allowed to form. And finally, the most unsettling possibility of all, the one that does not try to patch the existing rules, but instead asks whether the rules themselves, as we have written them, were ever complete to begin with. Some physicists have begun to seriously entertain the idea that our understanding of entropy and the second law, built almost entirely on observations made within a slow, steadily expanding, relatively gentle universe, may simply not generalize cleanly to the extreme conditions of the earliest moments after the Big Bang. Under temperatures and densities so extreme that our current laws of physics begin to strain and bend, perhaps the relationship between disorder and time does not behave the way our comfortable everyday intuition assumes it should. Perhaps entropy itself, in that violent newborn moment, increased through a different language entirely, one where complex structure was, paradoxically, the more probable, more natural outcome rather than the less probable one. This is not a comfortable thought for physicists because it does not offer a tidy solution. It does not hand us a new particle to search for or a clean equation to test in a laboratory. It simply asks us to consider the possibility that one of the most trusted, most foundational laws in all of science, a law so reliable that engineers build bridges and reactors and rockets on its back without a second thought, may have an asterisk attached to it. A footnote that reads, valid for most of cosmic history, exact conditions at the very beginning still under investigation. Think for a moment about what that really means. The second law of thermodynamics is not simply some obscure rule tucked away in a physics classroom. It governs the slow decay of stars, the cooling of your morning coffee, the wrinkles that gather on human skin, the quiet, patient march toward an ending that every living and non-living thing in this universe ultimately shares. If even a sliver of doubt exists at the very root of that law, in the earliest, most extreme moment of cosmic history, it does not erase the law for the rest of time. The coffee will still cool, the stars will still burn out, but it does suggest something far stranger, that the rules governing time, order, and decay may not be as universal, as unshakable, as eternal as we once believed. They may simply be the local customs of the particular cosmic neighborhood we happen to live in, valid here, valid now, but perhaps not valid everywhere, and perhaps not valid always. There is a particular kind of vertigo that comes from realizing this. A quiet, intellectual kind of fear that has nothing to do with monsters or shadows and everything to do with the ground beneath your feet shifting just slightly. We like to believe that physics gives us bedrock, an unmovable foundation beneath the chaos of daily life. Gravity pulls down, entropy increases, time moves forward. These are not opinions. They are supposed to be facts as solid as stone. And yet here, at the very edge of observable history, in light so old it predates almost everything we call familiar, we find a crack running straight through that bedrock. Not a crack that destroys the foundation entirely, but one that reminds us, with brutal honesty, that we built our entire understanding of time, order, and chaos by studying a universe that was already billions of years into its story. We arrived late to the play, and we have spent centuries assuming we understood the entire script simply because we watched the second half so closely. Perhaps the deepest lesson hiding inside the over-organized galaxies of the early universe is not really about thermodynamics at all. Perhaps it is about humility, the same uncomfortable humility a child feels the first time they realize their parents existed, fully formed, with entire histories, decades before that child was ever born. We look at an old photograph of our parents as young adults, laughing, full of plans, completely unaware of the family they would one day create, and something in us quietly recoils, because for a brief, dizzying moment, we are forced to confront the fact that the universe did not begin with us. It existed, fully, urgently, dramatically, long before we ever opened our eyes to witness it. Now imagine that same uncomfortable realization, scaled up not across one human lifetime, but across the entire history of existence. We are, in cosmic terms, the child staring at the old photograph. Except the photograph we are staring at shows a universe that appears to have been further along, more developed, more organized than the story we were told should have been possible at that age. It is as though we found a picture of our own universe as an infant, only to discover it was already standing, already walking, already carrying the early signs of structure we assumed could only emerge much, much later. Maybe time itself does not behave like the single, smooth, predictable river we imagine it to be, a current flowing steadily and uniformly from order into chaos, page after page, chapter after chapter, in perfect linear sequence. Maybe time, in its earliest, rawest form, behaved more like a held breath, compressed, tangled, capable of producing in an instant what should have, by every rule we trust, taken eons to build. Maybe the arrow of time was not fired cleanly from a single bow at a single moment called the beginning, but rather emerged gradually, imperfectly, from conditions so extreme that our tidy categories of order and disorder simply had not finished settling into their familiar roles yet. We are not here tonight to tell you that the second law of thermodynamics is false. It is not false. It remains one of the most rigorously tested, most reliably confirmed principles in the entire history of science, holding steady through every experiment, every reactor, every star we have ever measured. But we are here to remind you that even the sturdiest laws of physics were written by minds standing inside a universe already billions of years deep into its own unfolding story. Minds trying to reverse engineer the rules of a game by watching only the later innings. And every so often, the universe hands us a fragment of evidence so strange, so early, so impossibly mature, that it forces even our most trusted laws to whisper a quiet, humbling admission. There may be a first chapter we have not read yet, written in a language entropy itself does not fully understand. So the next time you watch ice melt in a glass of water, or feel the slow ache of years settling into your own body, remember that somewhere in the deep, ancient light still arriving from the edge of time, there are galaxies that appear to have skipped the slow, patient queue the rest of the universe was forced to wait in. They got there early, they got there organized, and no one, not yet, can fully explain how. Perhaps that is the final quiet truth hiding beneath all of this. The universe is not obligated to make sense to us on our schedule, using our intuitions, built from the small, fragile patch of time and space we happen to occupy. We built our laws by watching the middle of the story, and now, staring back toward its opening pages, we are discovering that the beginning may have been written in a far stranger, far more elegant hand than anyone dared to imagine. Disorder may still be the destiny of everything that exists. But destiny, it seems, is not always the same thing as origin. And somewhere between the silence before the Big Bang and the slow, certain decay we call entropy, there may be a moment, brief, violent, and almost impossibly organized, that simply refuses, for now, to follow the rules we were so certain it had to obey. And so we are left standing at the edge of our own certainty, looking out at a sky that remembers a childhood we never witnessed, holding evidence of an order we cannot yet explain. Perhaps one day a new equation will arrive, quietly rewriting the opening chapter of physics, smoothing the wrinkle, closing the gap, restoring the comfortable feeling that we always understood the rules from the very first page. Or perhaps the gap will simply widen, year after year, telescope after telescope, until it becomes impossible to ignore that the story of time itself may have more than one beginning, more than one voice, more than one law, quietly operating beneath the one we were taught to trust without question. Either way, the light is already here, already arriving, already waiting patiently in our instruments for someone bold enough or humble enough to finally listen to what it has been trying to tell us all along.